I will give you a very simple explanation of convolutional neural network without using much mathematics so that even a high school student can understand it easily. Let's say you want the computer to recognize the handwritten digit 9. The way computer looks at this is as a grid of numbers. Here I'm using minus 1 and 1. In reality, it will use RGB numbers from 0 to 255. The issue with this presentation is that this is too much hard-coded. If we have a little shift in digit 9, for example, 9 here was in the middle, but in this case it is in the left, and the representation of numbers just changes. It doesn't match with our original number grid, and a computer will not be able to recognize that this is number 9. There could be a variation since it is a handwritten digit. There could be variation in how you write it, which will change the two-dimensional representation of numbers, and again, you will not be able to match it with the original grid. So we use artificial neural network for this kind of case to handle the variety. In this deep learning series, we have already looked at artificial neural network video on handwritten digits recognition. If you have not seen that video, please make sure you see it so that your fundamentals on artificial neural networks are clear. In that, we created a one-dimensional array by flattening the two-dimensional representation of a handwritten digit number. And then we build a neural network with one hidden layer and output layer. And this dense neural network will work okay for a simple image like handwritten digit. But when you have a bigger image, let's say this.
Yeah, so just to make sure, so what we're doing in here is that it's an image, and from here, um, we can say this is a one-dimensional image, meaning it is not RGB, it is a grayscale. So let's say it is the channel is one, so it is grayscale. What we are doing is we're flattening, so it's a two-dimensional. Think of it as if we are breaking it into puzzle pieces and then putting it as a one row. So that's the thing. So we flatten it as a one-dimensional, and we feed into a deep neural network. So we call this as a fully connected layer. So the image, which we will pass it through a convolution layer, and then now we have a one-dimensional array that becomes an input to the fully connected layer. I'm gonna explain this later in the slides, and then it's gonna go through all the neurons, and then at the activation function, I'll be explaining later. It's gonna predict the output. So yeah, that's what he's explaining.
Neural network will work okay for a simple image like handwritten digit. But when you have a bigger image, let's say this little cute looking koala, the image size is 1920 by 1080. We have 3 as RGB channel here, one for red, green and blue. In this case, the first layer neuron itself will be 6 million. If you have, let's say, hidden layer with 4 million neurons, you're talking about 24 million weights to be calculated just between the input and hidden layer. And remember, deep neural networks have many hidden layers. So this can go easily into like 500 million or 1 billion of weights that you have to compute. And that's too much computation for your little computer. See, my rabbits are getting electrical shock because it's just too much to do. So the disadvantages of using ANN or artificial neural network for image classification is too much computation. It also treats local pixels same as pixels far apart. If you have koala's face in a left corner versus right corner, it is still a koala. Doesn't matter where the face is located. So the image recognition task is centered around the locality. Okay. So if the pixels are moved around, it should still be able to detect the object in an image. But with ANN, it's hard. So how does human recognize this images so easily? So let's go into the neuroscience little bit and try to see how we as humans recognize any image so easily. When we look at koala's image, we look at the little features like these round eyes, this black prominent flat nose, this fluffy ears, and we detect these features one by one. In our brain, there are different set of neurons working on these different features, and they are firing. They are saying, "Yeah, I found koala's ears. Yes, I found koala's nose," and so on. Then these neurons are connected to another set of neurons, which will aggregate the results. It will say if in the image you are seeing koala's eye, nose, and ears, it means there is a koala's face in the image. Similarly, if there is koala's hands and legs, it means there is koala's body. And there are different set of neurons which are connected to these neurons, which will again aggregate the results, saying that if the image has koala's head and body, it means it is koala's image. Same thing with hand-written digit 9. There are these little edges which come together and form a loopy circle pattern, which is kind of like a head of digit 9. In the middle, you have a vertical line. At the bottom, you have a diagonal line. Sometimes you don't have diagonal line at all. But we know that whenever there is a loopy circle pattern at the top, vertical line in the middle, diagonal line in the end, that means digit 9.
As students, we're constantly evaluated on the quality of our writing, on essays, homework.
So how can we make computers recognize these tiny features? We use the concept of filter. In case of 9, we have three filters. The first one is the head, which is a loopy circle pattern. In the middle, you have a vertical line. In the end, you have a diagonal filter. So we take our original image and we will apply a convolution operation or a filter operation. So here I have a loopy circle pattern or a head filter. This filter right here. The way convolution operation works is you take 3 by 3 grid from your original image and multiply individual numbers with this filter. So this -1 is multiplied with this one is multiplied with this one, and so on. In the end, you get a result, and then you find the average, which is divided by 9 because there are total 9 numbers. And whatever number you get, you put it here. Now this particular thing is called a feature map. So by doing this convolution operation, you are creating a feature map. So you do it for the second round of 3 by 3 grid. Here I am taking a stride of 1. You can take a stride of 2 or 3. Also, you don't need to have 3 by 3 filter. You can have 4 by 4 or 5 by 5 filter. And then you keep on doing this for your entire number. And in the end, what you get is called a feature map. Now the benefit here is wherever you see number 1 or a number that is close to 1, it means you have a loopy circle pattern. So this is detecting a feature. In the case of koala, this will be eye or nose. Because for koala, eye, nose, ears are the features. So by applying loopy pattern detector, I got this one here in my feature map. I also call it the feature is activated. It got activated here. For number 6, it will be activated in the bottom in this area. If you have two loopy patterns, the feature will be activated at top and bottom. If you have a number like this, it might be activated in a different area. In summary, when you apply this filter or a convolution operation, you are generating a feature map that has that particular feature detected. So in a way, filters are nothing but the feature detectors. For koala's case, you can have eye detector, and when you apply convolution operation, in the result, see, you got these two eyes at this location. If the eyes are at a different location, it will still detect because we are moving the filter throughout the image. And they are location invariant, which means doesn't matter where the eyes are in the image, these filters will detect those eyes and it will activate those particular regions. Here I have six eyes from three different koalas, and they are activated accordingly. Hooray! The hand of koala is in this particular region. Therefore, when I apply hands detector, it will activate here. Now for number 9, and I'm just moving between number 9 and koala so that the presentation is simple enough and you still get an idea. In case of 9, we saw that we need to apply three filters: the head, the middle part, and the tail. And when you apply those, you get three feature maps. So I applied three filters, I got three feature maps. And this is how these feature maps are represented if you are reading an online article or a book. They are kind of stacked together. And they almost form a 3D volume. In case of koala, my eye, nose, and ear filters will produce three different feature maps, and I can apply convolution operation again. And let's say this time the filter is to detect head. By the way, the filter doesn't have to be 2D. It can be three-dimensional as well. So just imagine this first dimension is representing eyes, and the second slice is representing nose, and third slice is representing ears. And by doing that filter, you can say that koala's head is in this particular region of an image. So you are aggregating this result using a different filter for head, and now this becomes a koala head detector. Similarly, there could be koala body detector. And now we got these two new feature maps, where this feature map is saying that koala's head is at this location and koala's body is at this particular location. Then we flatten these numbers. See, in the end, these are like two-dimensional numbers. So we can flatten them. So convert 2D array into 1D array. And then when you get these two array, just join them together. After you join, you can make a fully connected dense neural network for your classification. Now, why do we need this fully connected network here? Well, you can have a different image of koala. See, my koala is sleeping, he's tired. So now his eyes and ears are in different location. Look at his ears. See, they're here. For previous image, the ears were in a different location. So that generates a different type of flattened array here. And you all know, if you know basics about neural network, that neural networks are used to handle the variety in your inputs such that it can classify those variety of inputs in a generic way. Here the first part where we use convolution operation is feature extraction part. And the second portion where we are using dense neural network is called classification. Because the first part is detecting all the features, ears, nose, eyes, head and body, etc. And the second part is responsible for classification. We also perform a ReLU operation. So this is not a complete convolutional neural network. There are two other components. One is ReLU, which is nothing but, if you have seen my activation video on the same deep learning tutorial series, we use ReLU activation to bring non-linearity in our model. So what it will do is, it will take a feature map and whatever negative values are there, it just replaces that with 0. It is so easy. And if the value is more than 0, it will keep it as it is. So you see, just look at the values. It's pretty straightforward. ReLU helps with making the model non-linear because you are taking bunch of values and making them zero. So if you see my previous videos in this deep learning tutorial series, you will get an idea on why it brings the non-linearity. Especially see the video on the activations in the same tutorial series. The link of this playlist is in the video description below. So you'll understand why ReLU makes it non-linear. But we did not address the issue of too much competition yet. My rabbits are still getting electrical shock. Do something. Because see, for this image size, if you are applying convolution, let's say with some padding, you're still getting same size of image. You did not reduce the image size. Sometimes people don't use padding, so they reduce the image size, but only little bit. So pulling is used to reduce the size. The main purpose of pulling is to reduce the dimension so that my computer doesn't get this shock. You know. So the first pulling operation is the max pulling. So here you take a window of 2 by 2 and you pick the maximum number from that window and put it here. So here check this yellow window 5182. What is the maximum number? 8. So put 8 here. Here what is the maximum number? 9. So put 9 here. Similarly here maximum number in green window is 3. So put 3. So you take the feature map, apply your pulling and generate a new feature map after the pulling. But the new feature map is half the size. If you look at the numbers, you have reduced your 16 numbers into 4. So it's too much saving in your computation. So how it will look for our digit 9 case when you apply max pulling? Well, you can do a stride of 1. In this case, we did 2 by 2 window and stride of 2. Stride of 2 means once we are done with this window, we move 2 points further, 2 pixels further. In this case, we can do one stride. So this is one stride. You get an idea. And we keep on taking max. And this is what we get. When our number is shifted, this is the original number where we got this max pulling map. When number is shifted, you get this pulling map. So still you are detecting the loopy pattern at the top. So max pulling along with convolution helps you with position invariant feature detection. Doesn't matter where your eyes or ears are in the image, it will detect that feature for you. There is average pulling also instead of max. You just make an average. 5 and 1 6 and 2 8 and 8 16. 16 divided by 4 is 4. So but max pulling is more generally used. But sometimes people use average pulling also. So benefits of pulling number one obvious, reducing your dimension in computation. The second benefit is reduce poor fitting because there are less parameters. And the third one is model is variant tolerant towards variation and distortion. Because if there is a distortion and if you're picking just a maximum number, you are capturing the main feature and you are filtering all the noise. So this is how a complete convolutional neural network looks like. In that you will have typically a convolution and ReLU layer, then you have pulling, then there will be another convolution ReLU pulling. There could be a number of layers for convolution and pulling. And in the end, you will have a fully connected dense neural network. In this particular case, the first convolution layer is detecting eye, nose, and ears. Many times you will start with the little edges. You don't even start with eye and nose. But here, for the simplicity, I have put them. But usually you start with edges, then you go to eye, nose, ears, then you go to head and body, and then you do flattening. Again, anything on the left hand side of this vertical line is feature extraction. So the main idea behind convolutional neural network is feature extraction. Because the second part is same, it is a simple artificial neural network. But by doing this convolution, you are detecting the features, you are also reducing the dimension. There are three benefits of convolution operation. The first one is connection sparsity reduces overfitting. Connection sparsity means not every node is connected with every other node like in artificial neural network, where we call that a dense network. Here we have a filter which will move around the image, and at a time we are talking about only a local region. So we are not affecting the whole image. The second benefit is convolution and pooling operation combined gives you a location invariant feature detection, which means koala's eye could be in the left corner, in the right corner, anywhere. We will still detect it. Third is parameter sharing, which is when you learn the parameters for a filter, you can apply them in the entire image.
Give me 1 minute and I'll show you how BigQuery can help you get insights from your data fast.
Benefit of value is that it introduces non-linearity, which is essential because when you're solving deep learning problems, they are non-linear by nature. It also speeds up training and it is faster to compute. Remember, value is you are just doing one check whether the number is greater than 0 or not. If it is greater than 0, keep the number, less than 0, make it 0. The benefit of pooling is that it reduces dimension and computation, it reduces overfitting, and makes the model tolerant towards small distortions. How about rotation and thickness? Because by itself, CNN cannot handle the rotation and the thickness. So you need to have training samples which have some rotated and scaled samples, some thick samples, some thin samples. And if you don't, you can use data augmentation technique. What is data augmentation? Let's say for handwritten digits, you take your original data set and then you pick few samples and then you rotate them manually. Or you make them larger or you make them smaller, thicker or thinner, and you generate new samples. By doing that, you can handle rotation and scale in convolutional neural network. Once again, here is a quick summary of what is convolutional neural network. You can take a screenshot of this image, put it at your desk if you're trying to learn CNN and computer vision. To summarize, you take your input image, then you apply convolution operation and value. Then you apply pooling, again convolution value pooling, and you can do this n number of times. After that, the second stage is classification, where you use densely connected neural network. Now, very important thing to mention here is these filters the network will learn on its own. In previous presentation, we saw that we applied these filters by hand, but this is the beauty of convolutional neural network that it will automatically detect these filters on its own, and that's part of the training. So when the neural network is training, or when the CNN is training, because you're supplying thousands of koalas images here, using that it will use backpropagation, and it will figure out the right amount of filters. It will figure out the values in this filter, and that is part of the learning or the backpropagation. As a hyperparameter, you will specify how many filters you want to have and what is the size of each of the filters. That's it. But you do not specify the exact values within these filters. The network will learn those on its own. And that is the most fascinating part about neural network in general. In the next few videos, we will be doing coding using convolutional neural network, and we will be solving variety of computer vision problems. So I hope you like this explanation. If you don't know me, I'm Dhaval Patel. I teach data science, machine learning, Python programming, and career guidance on my YouTube channel. If you are starting machine learning and if you are looking for a very basic beginner's level of tutorials, then I have a complete playlist. You can start with very basic Python and Pandas knowledge on this playlist.
So is everyone seeing my PowerPoint screen? Oh, let's see. Yeah. You're seeing my PowerPoint screen, right?
Yes, I can.
Okay, so this slide is adapted from University of Waterloo, and they explain it pretty well, and that is why I have adapted it. So as you have seen the video, a convolution layer is the central layer where it does all the computation. So what it does is it has a filter, and when the stride is given, and the stride is the number of values of how to move. For example, if the stride is 2, then the filter will move 2 steps at a time. So the filter will move, and it'll do convolving, and the output, as you have seen from the video, is called a feature map. And yes, so there's a filter, there's an input. Input can be an image or anything, and the output is a feature map. So let's talk about what convolution is. So let's say there's a various filters, and this filter here is 3 by 3, and the image is 6 by 6. And the thing we should know is this network is called convolutional neural network, but it doesn't really use a convolution. Most libraries use a function called cross correlation and not convolution. So just a fun fact. So let's see the process. So what it does is the filter, the stride is the number of steps. So you can see how the filter is moving on step by step. And we do the dot product at the input and the filter, and it'll move until it gets through all of them. And the output image, as you see, can be equal to the size of the input or greater, or so the size of the output is determined by the padding, and the padding is on the input image. We could put all the 0 pixel values around the inputs to preserve the input size. That's called the same padding, or you could do nothing, which is called valid padding. Okay, so you see there, this is a dot product. If the stride is 2, you can see how the convolution gives a different output.
What is the
So as you
stride in this sense? Because I know you're referring to it. Is the stride the way that you're sliding your window? Like, if stride
So
equals
the stride is the number of steps you're taking. Here, you see how the 3 by 3 red square is moved only 1 block. When the stride is 2, you see how it is moving 2 blocks.
Yeah.
So,
yeah.
so if the input is an image, we can say the stride is the pixel number of pixels. So a filter will move 2 pixels at a time.
Okay. And will it move like 2 pixels down once it reaches the end of the row? In that sense.
Yeah, once it reaches on the very right side, then it'll go back to the left and shift. If the stride is 2, move down 2 steps and then do all the same process until it reaches the very bottom right corner.
Okay. Is there a dimensionality for a result that like you're guaranteed based on the stride? Like, because you're doing the dot product here, you have a 3 by 3, your stride is 2, and you have a 6 by 6 matrix. So if you
oh yes, that's a good question. So if you that's called a valid padding. If you just do the convolution with a filter with a raw image, That's called valid padding, and the output feature map will be smaller than the input image as you have mentioned. But if you want to preserve the image size, if you want the feature map output to be 6 by 6, then you would use same padding, which you put all the zeros around the outer side of an image, and then in the library it does automatically how many zeros you need. But if you put all the zeros around it, it preserves the. If you do dot product, it gets smaller, but because there's extra zeros on the corners, it preserves the size of the input image.
Okay. All right. Yeah. Thanks. That was the question.
Yeah, no problem. So, yeah, so as you can see from here, the right side is a feature map and the left side is input. The top one is a filter, and you see how, yeah, as Matthew has mentioned, we see how the feature map is 4 by 4. So the size became smaller. But if you want to keep 6 by 6, then we will put zero paddings around the corners, around the edges. So the convolution, the output is now, as you can see on the right side, that's the output. And yeah, I think University of Waterloo made a pretty good slides. And we would repeat this for multiple times. And like, for example, this is because we have two filters. And the output, the dimension will match the number of filters. So because there's two filters, it'll be 4 by 4 by 2. So 2 is the if you think about image, you could sort of think as if it's a color channel. Not really color channel, but you could say like the dimension. So it's 2D array. I mean, not 2D array, but 4 by 4 by 2. Yeah, because there's two filters. If you have one filter like this, it's 4 by 4. Here, 4 by 4 by 2.
So the filter here, when we have like filter equals 2, the filter in this sense, like I know you referred to like the RGB before, and you had like the image or the video did. It was like 1920 by 1800 by 3, where I think RGB was the 3. So in that case, does the filter represent like color values in that sense?
That's a good question. So what would happen is, you know how Matthew, you can see how the filter is a two-dimensional array, right?
Mm-hmm.
So it's like a single sheet of paper. It's not like how should I say? Oh, on the bottom, the feature map, you see 4 by 4 by 2, right? It's like a box.
Yeah.
It's a three-dimensional.
Yeah, so it's a tensor.
Yeah, tensor is a multi-dimensional array in TensorFlow, and the top one is it's a 2D. What would happen is if you have RGB image where the input has a color channel, or if it's multi-dimensional, then the filter will be multi-dimensional as well. So if the input image is three-dimensional RGB, the filter will be, in this case, it'll be 3 by 3 by 3. So there's so that you could do dot product.
Okay. Oh, okay, and I get it. So when you had, like, for example, from the video, the image of the koala and how they represented the koala's image as 1920 times 1800 times 3, that 3 what represented pretty much one array for one color, another array for another color, and then another array for another color. So you have a tensor in that sense.
Could you repeat, please? I'm trying to, yeah.
Yeah, so like with RGB, to my knowledge, like you'd have 3 2D arrays
So yeah,
that are grouped together.
RGB is like this. So
Yeah, exactly. That's exactly what I'm trying to describe. I just couldn't get the right words.
Yeah, so it's you can see how they're separated 2D three of 2D arrays, and you
Mhm.
see this is the question that you might. I think this was your question.
Yeah, it was.
Filter is now 3D because the input is 3D. Filter is also 3D in order to do dot product like this. Now we're doing dot product of 3D.
Okay. Yeah.
So,
Okay.
did I answer your question or?
Yeah, that's good.
Okay, nice.
No problem.
So yes, so now previously we had one channel. The one channel in the image and sense could be described as grayscale, but now we have RGB color image. And because it is three-dimensional, we have a filter of three-dimensional in order to do dot product. And yes, so I'm not sure, but if you remember from the video, what it does after the convolution layer, so after the convolution process, so right now here's a 2D array. We would flatten, like make into a row array, and then we'll feed it into a fully connected layer. So you see how 2D array is now into one dimensional, one row array, and then it's feed into fully connected layer. So yeah, so you can see how should I say? So there's a filter. Once you do all the convolution, you can see how on the right side that's the number of neurons, and you feed it into the fully connected layer. And the yeah, it's basically the same. So the fully connected layer is, it's actually neural network. You can see a deep neural network. So it's after the convolution, once we extract the features, we're feeding into a deep connected layers. So what actually is happening is yeah, so the max pooling is so before the fully connected layer, as you can see, this is a fully connected layer on the left side. It's like a deep neural network. So after the convolution, we do max pooling, and many models have a multiple convolution layers and max pooling a layer. And so what is max pooling? So max pooling is we're extracting the maximum value from each subregion. So like for example, like if you have this on the red side, it'll get 3, 0, 3, 1. On the right, it'll be -1, 1, 0, 3. So you're taking maximum value. And the guy has mentioned it, and the reason why we're doing max pooling is because we want to avoid overfitting, and because we want to reduce the computational load. And as you can see, it is 4x4, but if we do max pooling, it's now 2x2, which significantly reduces the size of the input. That means less parameters into the training model. And because of less parameter, we're significantly reducing the computational load. Yeah, as you can see from the slides, max pooling makes fewer parameters to characterize the image, and the max pooling is basically summarizing all the input features by taking out the maximum value. And as the guy has mentioned, there's also minimum pooling and average pooling. Average pooling is you take the average, minimum you take the smallest value. And typically we use the max pooling because it's actually most significant, especially on the images. So yeah, the CNN, the fully connected layer, yeah, so reducing the number of connections, shared weight on the edges, and max pooling. Yes, max pooling further reduces the complexity because it reduces the size of the input. yeah, so as you can see, if we do the new, yeah, so after the filtering, the max pooling, you see how it is, um, rather than 6 by 6, it is now 2 by 2. If the subregion is 3 by 3, so we're taking the maximum value. And the numbers are different because we have a two filters, and that is why. So we're taking the subregions and taking the maximum value out. Oh yes, so this is so as I have mentioned, so the output image is smaller than the original image, and the number of channels is the number of filters. Yes, so what happened is if we have two filters, let's say the output feature map is 2 by 2, and if the number of filter is 10, then the output will have a dimension size of 2 by 2 by 10. So the channels depend on the number of filters, and so here we're seeing 2 by 2 by 2 because we have two filters. And yes, flattening. So on the very right is a fully connected network, which is basically deep neural network. So you're seeing the feature map, and we would flatten, and that's why you're seeing 8 pixels, 8 values, and we'll feed it into the fully connected network. And in the between is called the hidden layer, and each layer gets weights and bias. And once we learn the and there's a loss function as well for CNN. Typically in an image we use a loss function called the cross entropy loss, and after comparing the difference between the actual value and our output, it'll update the weights and the bias, and that's called a stochastic gradient descent. And that's a backpropagation algorithm where we update weights and bias. So this is CNN in Python. So what happened is there's the input, and we're doing convolution and max pooling twice. So this is our Keras library. So according to here, we are the input shape is 28 by 28 by 1. So that's the grayscale image. And we are the filter is 3 by 3, and the number of filter is 25. So, and then yes, that's how we do max pooling. So basically, we're add function adds each layer. So we first add the convolution layer, and then we add the max pooling layer. So as you can see, it is extracting the maximum value, and the max pooling is 2 by 2. Okay, so yes, so the original input is 28 by 28 by 1 because of grayscale. And as you have seen from the previous slide, the channel gets the number of filters, and that is why it is 26 by 26 by 25. And the reason why it is 26 and not 28 is because, as Matthew have questioned, this is a valid padding where no padding is involved. And that is why the number of the size got smaller slightly. And then we do max pooling, and because it is 2 by 2, the size gets the half of the size. That is why it's 13 by 13, but the channel is still the same. And how many parameters for each? Yeah, so that's the convolution. And same here, there's no zero padding, that's why it got slightly smaller, 13 to 11. and we do max pooling, so divided by 2, it's 5. And flatten, yes. So we add a flatten, and then we feed into a fully connected layer. And what happened is, so at the dense, we're having 10 neurons, and then the output, according to this code, is 100 classification. And the activation is a softmax, and the activation is a ReLU. So what ReLU does is, so each layer, we add the activation function. What ReLU does is, if it's less than or equal to 0, it becomes 0. If it's positive, then it remains positive. And what softmax does is it returns a probability when the input is given. So that's the activation function. And yeah, the output is given. So that's the CNN in the Keras library. So yes, that's my presentation. And thank you everyone for joining. And if you have any questions, please feel free to ask questions. And I hope I hope I did well on explaining. But yes, feel free to ask me questions.
So, what are some other tasks that convolutional neural networks could be good for? Because I know they can be good for classification tasks and identifying, like through images. But what else could they possibly be good with?
So convolution can actually be used for. I actually recently realized this. You can actually use for um, continuous prediction, like a stock model prediction. You can actually use it for the stock model prediction. Like as it is a linear prediction, I was expecting uh use a simple gradient descent, but you can actually use convolution as well.
It's interesting.
Yeah, prediction. And the for me, I primarily use an image. So yeah.
Oh, all right. Thanks.
Yeah.